Well, Glenn 30s, here we go, chapter 14.3 on electrolytic cells. Now, we do have a new name for a new type of cell here. We've only been looking at spontaneous cells called voltaic or galvanic cells so far. The electrolytic cell is the name we give to the ones that are non-spontaneous. Now, you might be asking yourself, why the heck would I ever want a battery that is non-spontaneous? Well, with this, there are other applications or technologies to which we do get some other perceived benefit other than the electrical energy. A first easy one is a rechargeable cell. All right, your lithium-ion battery that you have in your cell phones that you guys could not live without. It behaves as a voltaic cell while it is just charging and running all of your various photo apps there, your Snapchats, your Instagrams, your TikToks, and all those other things that I will never ever understand. But at night, when it's time to recharge that, well, we need to supply energy. To make the reaction reverse would be non-spontaneous. This should make sense given what we already know about thermochemistry and those activation energy curves. There's always one that is easier and one that is harder. This is not dissimilar. So, when we take a look at our theoretical cell potentials and we calculate these things and predict them to be negative, then we must supply that deficit or negative energy with some other source. Now, it could be another battery, not overly efficient, or maybe some sort of generated power supply like plugging it into your wall. This battery will act like an electron pump. What it's going to do is force the electrons against their nature. Instead of from Ra to OA, it's going to force them to go the other way. This is because your power supply has a greater potential difference and it has the ability to force this reaction that wouldn't occur on its own. Your electrolytic cell still has the same stuff. It has an electrolyte, it has electrodes, it has a power source which is new, and it may or may not require a salt bridge or a membrane. So we can make these look visually similar, or we can make them look visually different. So take a look. Here's the two cells. Here's your galvanic cell. This is what you've been working on for the last few days, and it should make sense. All right. We have at our cathode our SOA, and of course it wants to undergo reduction, and so it's going to pull electrons spontaneously from the SRA and our oxidation candidate at the anode. And so we see this movement from negative electrode to positive electrode. The electrolytes and salt bridges are all there. These are exothermic, easy to run. Cell potential is positive. They are spontaneous. And we get this easy supply of chemical to electrical energy. The electrolytic cell is a little bit different. It does have a couple of subtle changes. All right? You'll notice that we still have the anode, that is still the SRA, that is still the site of oxidation. At our cathode here, this is still the SOA, this is still the site of reduction. Note that the two things are still the same. Okay? The one thing you will notice as a subtle difference here is the signs have now changed. Remember, we said that in our galvanic cell, we called it negative because it was kind of the source of the electrons as we went over and consumed them with those positive ions at the cathode. Not the greatest definition, but it kind of made sense for the signs. In this case, the signs flip because you're using something else. In this case, you would have your OA below your RA, and so it doesn't have the ability to gain those electrons spontaneously. So we have to use something that's going to force this. And so we hook it up to a power supply, and we hook it up to the leads of that power supply. There are positive and negative leads on this power supply. So let's just keep things really, really simple. If I want electrons to leave this, what part of my power supply should I hook it up to? The attractive positive or the repulsive negative? Very obviously, it has to be the positive. So notice with this wire, I'm really just extending my positive pole of my power supply. So it's just an extension of that little positive that you guys see right here. So that's why there's the sign change. Same thing happens here. All right, if I want electrons to keep moving away from this, then they should flee this negative and move towards here, and it's really just an extension of this pathway. So I need to use this power supply and its polarity to draw electrons in the direction that I want to make this non-spontaneous reaction work. So please realize that anode and cathode have the same definition, the same OA and RA, the same oxidation and reduction. That is all the friggin' same. The only difference is you've hooked it up to a separate power supply with its own unique polarity, and so we see for the non-spontaneous, the charges on our electrodes change. That is the only subtle visual difference that you see with respect to your electrodes. So, we should go through, we should take a look at all of this in a little bit more detail. You can see that we have a slightly different look to these cells. All right, both electrodes are sitting in the same electrolyte solution. It does not mean that a porous membrane or boundary or salt bridge couldn't be shown here. All right, but in most cases it's not necessary due to the non-spontaneous nature. Something else that we see that's a little bit different is what the bleep is this? All right, this is the schematic in circuitry for a battery symbol. Each short bar and long bar represents one cell. Therefore, multiple bars equals multiple cells and therefore a battery. Recognize the symbol, and it does have a specific notation that I want you to remember. The long bar is always positive. The short bar is always a negative. Well, if the long bar is attached to this one, then this is positive, and therefore in an electrolytic cell must be the anode. All right, on this side you are connected to the negative part of your battery, and so in an electrolytic cell, because those signs changed, this side must be the cathode. All right, they are both inert carbon electrodes. Obviously what we have going on here is going to be stuff without a particular solid state for us. And so let's see if we can figure out from the question what is ultimately going on. We can still solve these with the entities method. Or if we were given a cell notation, we could certainly interpret that as well. But it says, during the electrolysis of a copper 2 sulfate solution, what products appear at the two inert carbon electrodes? Don't forget to include water in these. Water, now with the non-spontaneous reaction, becomes a much more frequent player, so we want to be careful with some of these. So let's look at our entities. All right, if I have a copper 2 sulfate solution, I have copper 2 plus ions, I have sulfate ions, I have water, and I have my inert carbon electrodes. Inert means it doesn't react, so include it or don't. Doesn't really matter. It shouldn't play a role. I don't see any other possible entities. Go back to your handy-dandy table, all right, and see if you can list all of your OAs and all of your RAs. Okay, so for this one, copper 2 plus should be an OA. Sulfates on its own doesn't appear anywhere, but I do see it with water as a potential OA. Water on its own is an OA or a potential RA. Carbon isn't anywhere on your list, so it's not going to play. And sulfate and copper do not play on the right-hand side of the table. So there you go. You have 3 potential OAs, 1 potential RA. That makes figuring out the RA pretty easy, and lo and behold, there's your water. Okay, for your strongest oxidizing agent, copper 2 plus is going to be that guy. So let's take a look at the oxidation reduction pathways here. All right, reduction of your SOA always happens at the cathode. And so that means at the cathode, copper 2 plus and 2 electrons being gained are reducing to solid copper. So whatever I've decided is my cathode should have copper being reduced there. We can also include our reduction potential of 0.34 volts. That is also right off your table. Oxidation. That is of your SRA, and therefore is happening at the anode. Okay, for that one, it is water. We haven't seen this before, so find water as your SRA. Water, water, water. There it is. Okay, and so we just want to write this oxidation half reaction, and we'll want to sign flip this particular value. So we can write that one out where we have 2 H2O liquid giving up 4 electrons, 4 hydrogens, and 1 oxygen. Kind of ran myself out of room here, sorry guys, but that'll be a negative 1.23 volts when we take a look at this one. Okay. We can finish off this reaction. We can take a look at what's going on for a net redox reaction, but to answer the question, we don't really even have to go that far. We're just looking for what the products would be at anode and cathode. All right, it said what products appear at the 2 inert carbon electrodes. This carbon on the right is my cathode. All right, negative sign, we were able to determine that quite early on. This means that copper 2+ ions in solution are bumping, gaining those 2 electrons as they're moved over to it to form atoms of solid carbon. Copper, pardon me. Copper on this carbon electrode. All right, so my cathode, just like it did before, is gaining mass. It just happens to be copper mass that is being gained here. What's happening on the other side? All right, water is oxidizing to electrons, hydrogen, and some oxygen. So we should start to see some bubbles appearing. All right, what would those bubbles have to be? They should be O2 gas. We should also start to see the proliferation of H+ ions in this area as they are also produced as the electrons are pulled and moved over to the other side by that power supply. So a couple of things that we can notice would be a lower pH on this side around the anode to begin with, and also some bubbles that start to appear, which should be testable for O2. Okay, we have a visual test for copper as it's a reddish metal. We can take a look at one last thing here. We can take a look at what that cell potential will be, and we can find out that when we add these two things here, E cell will be negative 0.89 volts, so non-spontaneous. This will not happen on its own, so again, that's why I need my power supply. So, take from this, things are very, very similar. A little bit of work to do, but it actually was kind of easy with the battery symbol as to which was which for cathode and anode. And again, from our OA and RA side, we can certainly identify them as well. Okay, there you go. I will do one more example and guide you towards some examples that you can look at as well in the textbook in the next part of the lesson.